Hey everybody, here we are with section 2.2. We are officially out of the review stage now and moving into pre-calculus topics. So a lot of this, although you should have been exposed to at some time, but now we're going to go to it in a little more depth. Look at graphing functions by plotting points with a graphing calculator, piecewise defined functions, the vertical line test, and equations that define functions. Most important way to visualize a function is through its graph. In this section, we'll investigate in more detail the concept of graphing functions. We'll look first by plotting points. Graph of a function, we plot the points x and f of x, that's your x and your y, in a coordinate plane. And we have an input whose y coordinate is the corresponding output. So our input and output. And here we have our set notation that says x comma f of x, which is your x and y, such that x is an element of A, and that's the domain. So a function in the form of y equals mx plus b is called a linear function. This is, and notice I said y equals mx plus b, also f of x. F of x and y are interchangeable because its graph is the equation of y equals mx plus b, which represents a line. M is your slope and your b is your y-intercept. A special case of linear functions occurs when the slope is 0. Obviously, when the slope is 0, this whole term will be wiped out. The function f of x equals b, that's what you would have left if m is equals 0, is called a constant function, and it has a horizontal line, y equals b. Here we have our horizontal line, just y equals 3. That's because our slope here is 0. And the slope is 0 whenever you have a horizontal line is a very important concept to know for calculus, that when you have a horizontal line, the slope is 0. That's why they're emphasizing this so much here. And here we have f of x equals 2x plus 1 over on this other graph, and it's just showing you that it goes through 1, which is the y-intercept here. 1 is the y-intercept. And then from that point, you're going to rise to and go to the right 1. So you go up to the right 1, and that'll give you your 2 over 1 slope. So we're going to look at some of these special graphs of the following functions. Now, the graphs that we're covering right here are graphs that you need to study and know upon sight when you see them. Here they have us making a table of values, and what that means is you're going to take these numbers and you plug them in for x, and then you get your values. And they did that with x squared, x cubed, and the square root of x. Now, you don't need to memorize or know this table of values. This could be any table of values, whatever you decide to put in. I will point out over here, notice they have plus or minus 1/2 being 1/4, plus or minus 1 is 1, and that's because it's a symmetric graph. And the y values are the same for the positive and negative values of x. And you'll see this a little more in the graph coming up. Here are the graphs. See, like I said before, my 0 value is here, but my 1 value, notice right here, my y value is the same for plus or minus 1. So here's your x value, -1. Here's your x value, +1. And the y values are both 1. So that's why the table before that had the plus or minus and then the same value. This is a symmetric graph, and here we have our axis of symmetry right through the middle of it. This particular graph here, not the numbers that are along it, but what it looks like right here is a parent function for quadratics, and it's something that you should recognize when you see it. Also, here we have g of x equals x cubed. This is a cubic function. When you see this, this is the parent, they call this the parent function of the cubic functions. G of x equals x cubed. Now, it doesn't matter whether it's g of x, f of x, h of x, or y, okay? That part's not important. The important part is that when you see a graph that looks like this, that you recognize it's a cubic graph. Likewise, when you see a graph, again, could be f of x, could be h of x, could be g of x, could be y equals. When you see a square root of x, this is the graph that you're looking for. This is the parent function, square root of x. So I'm going to say it again. You should know these graphs upon visually seeing them. Go, oh, that's a quadratic. Oh, there's my cubic. Oh, here's a square root graph. And that's why they're called parent functions. So important to recognize. Now we're going to take a quick look at using a graphing calculator, and I know that I said that we would use graphing calculators periodically, and this is one of those periodic times. It's just important for you to be familiar with it. It's not going to be a big emphasis though. Very convenient to use a graphing calculator when you know how to use them, that is. Here we have a cubic function, and why did I say it's a cubic function when it has a cube and a square? Well, because the degree is 3. The highest exponent is 3. So we're going to take a look at this function. Okay, so they're showing you that in your graphing calculator, you're going to put y equals x cubed minus 8x squared. And you'll see that your standard window, and that's what is automatically put in your graphing calculator, generally is set up from -10 to +10, from -10 to +10 also on the y. Now, you can change that, and you should change that. Obviously, here I can't really see much of my graph when it is that. So you have to start getting comfortable with looking at these boundaries and being able to adjust them. So we have to expand our vertical axis to get a better representation of the graph. We don't really need to expand our horizontal representation. This could still be -10 to +10. But here, if I expand this to 100 to -100, now I get a beautiful graph. Now you might say, well, it doesn't quite look like a cubic. It does, though. In fact, if you take a look at this and you see how before, I'm going to, let's see, I'll use a blue color. Before we had something that would come up and would hit this, and then it would go up this way. Well, all we did was really pull this section right here down to here. Notice it still comes up, and it still does this method here where it has 1, 2 areas that it changes the way that it looks. And I'll get into more of the technical terms for that in a little while. All right, piecewise functions. Piecewise functions, exactly what it sounds like. I'm going to take part of this graph and use it for this domain, and then I'm going to take part of another graph and use it for another part of a domain. So this piece is here and that piece is there, kind of like a puzzle. Okay, so again, different formulas on different parts of its domain. So here we have a piecewise function. So the important part of looking at a piecewise function is to just take each line by itself. So basically, I'm going to do another little drawing over here on the side. I have an area that is smaller than or equal to 1 and an area that's greater than 1. So if I have my coordinate plane here, oh, I'm so sorry. Let me see if I can straighten that line out a little better. I need to take some art lessons. Okay, so here we have going across. That's a little better. Okay, so now I have the number 1. I'm going to put 1 right here. Okay, so this is my number 1. All right, so this tells me that before or equal to 1, I'm going to use this function. So before and equal to 1, this area right here, let me highlight it with, I'll highlight it with like maybe a light green color here. This area right here, I'm going to use this function, okay? And then anything that's bigger than 1, I'm going to use, let's use a blue. I'm going to graph it over here, and that would be this function. Okay, so when I look at this, I know that this is right here is a quadratic, and it's my parent function. Hopefully you remember that parent function, and it will look like this. And again, to the best of my ability, comes up a little bit more than that, like this. Okay. And this 2x plus 1 has a y-intercept at 1 and then the slope of 2. We looked at that earlier. So y-intercept of 1 would be right here. And then from that, it goes up 2 and over 1. Okay, so it's going to come across like this and a little straighter than I can draw. Okay, so those are the two on top of each other. Now, the problem is I'm only going to use less than or equal to 1 for the blue function. So anything that's after 1, I shouldn't have this here, okay? So I shouldn't have this part right here because it's actually after my domain that I'm looking at. And the same for my 2x plus 1. I only want where it's greater than 1. So I only want this part. So I don't want any of this right here for that function because I don't care about that part of it because it's not in this domain. So my graph should actually come up, and I'm going to do my best to highlight this here. My graph should come up right here. I'm following this one because it's before 1. And then as soon as I get to 1, I am following this other one. So that would be my final. Now, their picture, I'm sure, is much. Okay, so at first I thought I might have hit the backwards button, but they brought up this slide again just so they can show you this function. This is the one that I showed you before. This is the parent function, but we only want to use it until it reaches 1. So we're only using this part right here. So don't worry about these two right now. We're not looking at these right now. This has nothing to do with the problem. We're only looking at this one. All right, let's take a look at the next slide. Same here, they just brought this same slide up again so that you could take a look at this one over here. And so I'm going to take a look at after 1, this part of my line is the only part that I want to use. So when we put that together, When we put that together, we have this going to 1, 1, and then it jumps up here because this is where the second line was. See, I told you their picture would be better than mine. And that would be the second part. So this is actually what the graph will look like for this piecewise function. I'm going to use the first part, less than or equal to 1, and then after 1, I'm going to use this graph. Okay, this dot here, and I should emphasize that also, this dot right here on the graph means that I am including 1 in with the x squared. See, it's less than or equal to. That's why that's a closed circle. And then this is an open circle up here because I'm not including 1 in the second part of my graph. So see, there's no line under here, so that's why there's an open circle. Okay, so now we're going to take a look at the greatest integer function. Some of you probably have seen this and some of you may have not. I've had a mixed bag usually when I teach pre-calc of people who have studied the greatest integer function and people who did not. So the greatest integer function is the greatest integer less than or equal to x. The biggest integer smaller than what the x is on the inside. Okay, so for instance, let's take a look at the greatest integer function of 2. Well, the biggest integer that is smaller than or equal to 2 is simply 2. Look at the next one. What is the greatest integer function? What is the greatest integer of 2.3? Well, the biggest integer smaller than this number is 2. Let's look at the next one. What is the greatest integer smaller than this number? Well, the biggest integer smaller than this number is 1. What is the greatest integer smaller than this number, 0.002? The greatest integer smaller than 0.002 is 0. Now this is where it gets a little tricky. You really have to think about your negatives because you want to know what's the biggest integer smaller than negative 3.5. Well, we're tempted to say negative 3, but negative 3 is bigger than 3.5, negative 3.5. So we can't say that because it says specifically we want the greatest integer less than or equal to negative 3.5. So the greatest integer less than or equal to negative 3.5 is negative 4. So a lot of times I say, think about your temperature and smaller numbers are if you have a vertical line, I'll draw this over here. Let's see, we'll use blue. Let's say I have a thermometer here. And then my smallest numbers are at the bottom and my biggest numbers are rising to the top. So if I have a negative 3.5 here, I want to find the biggest integer that's smaller than this number. That means I have to go down. So I have to go down to negative 4. I wouldn't want to go to negative 5 because negative 5 is not the biggest integer smaller than this number. And I wouldn't want to go to negative 3 because negative 3 is bigger than negative 3.5. So it has to be my negative 4. And finally, if I have what's the greatest integer of negative 0.5? The greatest integer that's less than or equal to 0.5 is negative 1. So the greatest integer function is an example of what we call a step function, and it gets that name because it looks like a set of steps. The cost of a long-distance daytime phone call in Toronto, Canada to Mumbai, India is 69 cents for the first minute and 58 cents for each additional minute or part of a minute. So this is a typical example that we use to show greatest integer functions. Draw the graph of the cost in dollars of the phone call as a function of time. We're going to say C of t be the cost for t minutes, and we know that we're not going to have anything less than 0 minutes, so our graph is going to be greater than 0 because we're not going to document calls for 0 time because then you didn't make a call. So the domain would have to be bigger than 0 to infinity. I use a little logic there. So here we have our 69 cents from the information that they gave to us from 0 to 1. 69 cents for, remember, they said the first minute. So the first minute, we're charged 69 cents. Okay, and that's why we have the t is greater than 0 and less than or equal to 1. So for the first minute, it's that. Then after that, you're going to take that 69 cents and we're going to add 58 more cents. So you're going to be charged $1.27 from 1 bigger than 1 minute and then smaller and equal to 2. And this continues. I'm going to get charged 58 cents from bigger than 2 minutes to 3 minutes, and from 3 to 4 minutes, 3 of 58 minutes onto that 69 cents, and so on. So this graph looks like this, and again, that's why it's called a step function. So you can see the first minute is right here. The first minute is right here. Let me get up here and no, I wanna make my, it won't let me make my laser pointer be blue. I don't know why it won't, but it won't. Okay, so underneath from 0 to and including 1 minute, I am charged 69 cents right here. No matter whether I talk 10 seconds or 20 seconds or 40 seconds, as long as it's under a minute, this is what I'm charged. Once I go over 1 minute, it jumps up here and adds another 58 cents. And then I'm charged that amount maybe for 1 minute 10 seconds, 1 minute 30 seconds, until I get to 2 minutes. And the moment that I go over 2 minutes, it jumps up and I get charged another 58 cents. And then when it goes over 3 minutes, it jumps up and I get charged another 58 cents. Then when it goes over 4 minutes, it jumps up and I get charged another 58 cents, and so on. So that's why this looks like a step function. Now we're going to take a look at continuous functions. Now continuous functions have no breaks or holes in them. So obviously the last function that we looked at, the step function, is not a continuous function because it has some holes in it and it breaks. So examples 1 and 2 were continuous functions, but examples 4 and 7 are not continuous functions. And take a look in your book. Again, go back to your book. Examples 1 and 2 are continuous, 4 and 7 are not. So how do we know about continuous functions? Well, we do what's called a vertical line test. The graph of a function is a curve in the xy plane, but the question arises, which curves in the xy plane are graphs of functions? And so we need to see what graphs do we have that we would consider functions. So we can do what's called a vertical line test. Vertical line test is exactly that. I'm going to take a vertical line and I'm going to draw it everywhere on my graph. And as long as it hits that graph only once, then it passes my vertical line test. And I call it the graph of a function. However, if I come over here, I notice that when I get, and sorry, my lines again aren't that straight. I notice that right here and right here, it's hitting this graph twice. As soon as that happens, it's not a graph of a function. So each vertical line, x equals a, intersects a curve only once. Then exactly one functional value is defined by f of a equals b. But if a line x equals a intersects the graph twice, or 3 times, or more times, then the curve cannot represent a function because a function cannot assign 2 different values to an input. So we see here that it's hitting the graph twice, so this is not a graph of a function. But we see here, no matter where I go, as long as I draw a line straight, which again, I'm not doing a very good job of, this is a graph of a function. And then if I take a look at C, even though I have some areas where I have abrupt changes, I'm still only hitting there at one time. But when I get over here to D, I hit it here, I hit it here, I hit it here. So I'm hitting the graph multiple times when I draw vertical lines. So it does not represent a function. Any equation in the variables x and y defines a relationship between variables. So we have relationships here. Defines a relationship between y and x. Does this equation define y as a function of x? To find out, we solve for y, and we get this, which is, you should recognize as our parent function of our quadratic. We see that the equation defines a rule that when you have one value of y for each value of x. And here's how we express the rule. We can write y equals, or we can say f of x equals. But not every equation defines y as a function of x. Here, if I take the first one and I solve for y in terms of x, I can get y equals x squared plus 2. And all I simply did was get y by itself by adding x squared to both sides. So I could write this as f of x equals x squared plus 2. Now if we do the second one and we want to solve it for y in terms of x, I get y squared equals 4 minus x squared when I bring x squared to the other side. And when I take the square root, I will get plus or minus the square root of 4 minus x squared. Now this gives me 2 values of y for one value of x. So this does not define y as a function of x. And the reason again is that this says plus or minus, so it's given me 2 values instead of 1. So the key is one value. And here we have the graph showing the first one is a function, the second one was a circle, and that's why it hit the graph at 2 places at one x value. It hits it here and it hits it here in several places on that circle. Once again, these are some more functions in their graphs. This is your horizontal function, which this would be like y equals 5 or y equals 3 or something like that. Here's our y equals mx plus b, f of x equals mx plus b here. And this is our parent function for our quadratic. This is our parent function for our cubic. Notice our parent function for our fourth exponent on x, so we have x to the fourth. Notice it just flattens this out a little more right here. And same when I have x to the fifth, it flattens out my x cubed function graph here. So again, I'm going to say you should be able to recognize these. Now sometimes it's difficult to recognize this one from this one, but you should at least know that it could be a quadratic, it might be the fourth root, it might be the sixth root. Here are other parent functions that you need to become familiar with. So this is the square root of x, the square root of x. This is a cube root of x, again, because cube roots can have negative values, so it does have a range down here. And this is our fourth root, which looks similar to our square root, and this is our fifth root, which looks similar to our cube root. Now our reciprocal functions, here I have 1 over x will look like this, and 1 over x squared. The x squared makes it all positive, so that is why this part of the graph then comes up to this part, because I'm going to get a positive value. Same kind of thing with my absolute value function. When I take the absolute value of a number, it's always a positive number. So even if I take the absolute value of some negative x values, it comes up and becomes positive. That's why you get this V-looking graph for the absolute value. And then your greatest integer function we looked at before. You will move along till you get to a certain point, and then it jumps up, move along, and then it jumps up. So these are all considered parent functions of the graphs, and you need to be familiar with them.